The second step is rate limiting. So we don't care about the formation of the ester. We just focus on this step and compare the two oxidation steps of the two esters already formed. So I will draw now the chromic esters of the two alcohols formed on the left side. That's the chromic ester formed in the first step from the axial alcohol. That is the chromic ester formed in the first step of the mechanism from the equatorial alcohol. So which one reacts faster? This one or this one? I visited your campus and you showed me that some students, they use boros to well, take another. So what would you say? Which reacts faster? In the axial compound, there is 1,3-diaxial strain. This strain is not present in the equatorial one. And the strain is a driving force for the reaction. Therefore, the axial ester reacts faster, and therefore the whole reaction of the axial alcohol is faster. The release of strain is the reason for the kinetic difference of these two reactions. So for a multi-step mechanism, you have to know the rate limiting step. You have to consider the conformation, and here it's diaxial strain that is important. Let's go one step further. I told you that the second step is rate limiting. But how do we know that the second step is rate limiting? How can you determine by an experiment this afternoon in your lab that the rate limiting step is the oxidation and not the formation of the chromic ester? How could you do this? 30, 40 years ago, people developed this mechanism and they made these experiments. They found out somehow which step is the rate limiting step. What would you do? Here's space again for the mechanism without stereochemistry, just an alcohol in the first step forms the ester, and then in the second step This bond is broken and the ketone is formed. So how can we make an experiment to find out that step is rate limiting? Who has an idea? The fun about science is to think, to have own ideas, not just to learn facts from history. What would you make? Let's say you have time till tomorrow at noon, then you have to come back and tell me the results of the experiments. Well, if the second step is rate limiting, the breaking of this carbon-hydrogen bond should be important. Now let's change the strength of this bond by introduction of deuterium. If I have deuterium in that position, I still can make the oxidation, but the strength of the carbon-deuterium bond is different than the strength of the carbon-hydrogen bond, and that will have an effect on the rate. Which bond is stronger, the carbon-deuterium bond or the carbon-hydrogen bond? What have you learned? The carbon-deuterium bond is stronger. You can calculate in physical chemistry, so the CD bond is stronger than CH. If this bond is stronger, then upon introduction of deuterium, the rate of the whole reaction would decrease, and that is observed. So if I introduce deuterium at that position, the whole reaction gets slower, and that proves that the second step is rate limiting, because the deuterium affects only the second step, not the first one. If there would be no change in the reaction, it would be the first step. Because there is a change, a kinetic isotope effect, it's called. We know today that the second step of the chromic acid oxidation is rate limiting. So you see, this is a simple reaction, but if you understand it, you know a lot about chemistry. You know about the importance of conformation of molecules to talk about selectivity. You know that you have to know the mechanism, that you have to know the rate limiting step in the mechanism, the importance of strain on rate, and then you have to know of methods to find out the rate limiting step. And that method here is kinetic isotope effect. So I hope that's something that may be useful for you in general in chemistry. Are there any questions concerning this example? I give you a second problem, and then I go to the ion channels, then we talk about the second problem.